So, Filippo, now it's time. So let me first introduce you. Uh, First, it's our great honor and a pleasure to invite Professor Filippo Ubertini from University of Perugia, from Italian, to give us this keynote talk in this week. And Dr. Filippo Ubertini is a full professor of structural design at the Department of Civil and Environmental Engineering of University of Perugia, Italy, teaching structural analysis and design and earthquake engineering. He also serves as a coordinator of the international PhD program in civil and environmental engineering at the same university. Having graduated from University of Perugia in 2005, he went on to earn his PhD in civil engineering from the University of Pavia in 2009. As we mentioned, in 2008, he further enriched his academic experience as a visiting scholar at Columbia University in the United States. And throughout his career, he has authored over 150 papers published in highly impactful international journals. Actually, I just Google Scholar the related data. Filippo's H factor is as high as 50. It's very high. So, and Dr. Ubertini's research primarily revolves around the area of structural health monitoring, focusing particularly on smart materials, notably nano-engineered strain sensing silicon-based materials, as well as advanced signal processing and the application in bridge engineering, historic structures, and earthquake engineering. His expertise has led him to serve on editorial board of renowned journals like Mechanical Systems and Signal Processing, in addition to contribution to various other international journals. He has also been a member of the scientific committees of several prestigious international conferences. So without further ado, Filippo, please, floor is yours.
Thank you, Jing. Thank you very much. Thank you for the invitation, first of all, and thank you very much for the introduction. I'm really pleased to be here today, and I am happy that the attendance could connect, even if it's late, kind of late in China due to time change. So this talk is mostly about smart concretes research we have been doing at University of Perugia for the last about 10 years. But then I will also discuss a few new topics that around this one we are working on at the University of Perugia, including the 3D printing of the smart concretes, the possibility of shooting the concretes, and then an important project we have just started on smart masonry, and a little bit of smart pavements for way in motion. And finally, I conclude the talk. So the overall framework in which this talk frames is that of our aging infrastructure network. We all face similar problems around the world with our bridges and tunnels, reaching the end of their service life and being subjected to different types of degradation and deterioration phenomena. The problem in this structure is that damage initiates at the position where the damage is not visible. Think about corrosion in reinforced concrete or pre-stressed bridges. And then this damage propagates, but still it's not visible. And when it creates a significant reduction in performance, leading the structure eventually to local or global collapses, it's actually too late. So what we really want to do is spotting these kind of damages before they actually generate an harmful situation. So this is what my group at the University of Perugia basically works on. Our focus is in general structural health monitoring, which means using information coming from different types of sensing systems installed in structures to understand when the structural behavior is changing and when there are issues that may lead to local or global structural failures. I would say that the group is kind of divided into two parts. There is one part of the group mostly working on signal processing. Today, a lot of machine learning and AI research in this field we are doing, where the data comes from traditional sensors. So the innovative part is related to the algorithms of SHM, including the modeling part of the structures. And then there is another part of the group that is instead devoted to developing advanced sensing systems. So basically smart structural materials that can serve dual purposes. They can be structural materials, so sustain the loads, but they are also sensors. And typically they are strain sensors or damage sensors. This is what we do basically in the field of smart concrete, which is the topic I'm presenting you today. The smart concrete is a concrete that can provide the ability to sense a strain by outputting a change in its electrical properties. The smart concrete can also sense the damage, again, as putting in evidence a change in its electrical resistance. So what you see here are a couple of softwares that we have developed recently. Let me change this. I would like to reload this one. Anyway, it's not loading. A couple of software tools we have recently developed in the framework of traditional structural health monitoring. The one you see on the bottom left is a software that we have developed for ANAS, which is this symbol here. That is the biggest Italian, let's say, road managing authority. ANAS is now monitoring about 1,000 bridges, and they are using our software for damage detection. This one you see on the bottom right is instead a software that we call MOS, and that we use mostly for research purposes. I would like to reload this one. Let me see if I can do it. If I don't, that's okay. I'm trying to remove the pointer. Let's do like this. Okay. This is a software that we call MOS that we use for research purposes, which inside, it contains a lot of algorithms for novelty analysis and damage detection in different structural systems. So basically, it contains the part of our research devoted to the data analysis. However, yeah.
The screen we are seeing now is the poster instead of your slide.
So you haven't seen the slide so far?
Yeah, no. We are seeing the poster.
Because I have a double screen. That's probably the issue.
Yeah.
So let me see. Okay, let's do like this. So I'm sharing desktop 1.
Mm-hmm.
You see desktop 1? You still see the poster?
Yes, but that's fine, I think.
No. I mean, you should see the slides.
Yeah. Now we are seeing the slide, the first page of your slides.
First page?
Yeah.
Okay. So is now. Let me.
Yeah. Oh, it's good.
Is now working?
Yeah, it's working, but it's not in a full screen mode. We can still see,
okay, because you are seeing this one. So now it should be okay.
It's okay. It's good.
Okay. So this was what I was reporting before. Sorry for this. So this was the outline when I was discussing the topics. And
Yes.
This was the slide when I was mentioning that we all have the same problems in the world related to aging infrastructure and about the damage initiation and propagation leading to the collapse, which is what we want to avoid. I was saying that our group is at University of Perugia is devoted to structural health monitoring, which means using information coming from sensors to understand the structural conditions and to understand when a damage develops within a structure. I was saying that the group is basically divided into two parts. There is half of the group that is more devoted to developing algorithms for SHM, including a lot of machine learning and AI efforts, and part of the group that is instead devoted to develop innovative sensing systems for structural health monitoring. I was playing these two videos which now I comment. You confirm, Jing, that you see the videos, right?
Yes, we can see it very clear.
Okay. Yeah, this is an example of the research we are doing on data analysis and signal processing. This is a software on the bottom left that we have developed for ANAS, this symbol here, which is the biggest Italian road managing authority. ANAS is now installing monitoring systems on more than 1,000 bridges across the country, and they are using our software for novelty analysis and damage detection with an overall investment they are doing, which is in the order of 300 million euros. The other software you see in the bottom right here is a software that we call MOS, that we use in our group for research purposes, and that incorporates different algorithms from AI and machine learning for SHM. However, today I will not talk about this research. I'm just doing it to frame our group. I will talk about our research on smart materials, which are structural materials that can serve a dual purpose. They can serve the purpose of being structural materials and also the purpose of being sensors, strain sensors or damage sensors. In these regards, I put you here the website of the largest project we just started in my group, which is devoted to smart masonry, which is the Italian equivalent to the grant from the ERC. Then there is the webpage of our group and the YouTube channel of our group. All right, so the type of smart materials I'm talking to you about today, they kind of cross between a non-destructive evaluation and structural health monitoring. Non-destructive evaluation is basically the group of all techniques that we use to detect and quantify a defect in a structure by means of an inspection that we do periodically on the structure. Instead, in SHM, what we want to do is using data coming from sensors, which are permanently installed in the structure, to understand when the structural behavior changes and when there is a damage. Smart concretes, as a matter of fact, can be useful to speed up NDE, and of course, they can be pretty useful for structural health monitoring. So what are smart concretes? The way in which I like to introduce smart concretes is by recalling a famous axiom that is reported in the book by Chuck Farrar and Keith Warden. In their famous book on structural health monitoring, the authors stated that sensors cannot measure damage, and we need feature extraction to understand when there is a damage. Actually, the smart concrete is a technology that aims to challenge this long-standing assumption by creating a material that is a structural material, but also a damage sensor. Or at least it can provide, in the case when we use it for strain sensing, a more direct information to be linked to the damage condition within the structure. So to give you an idea of how well a material like this works, I'm showing you here an experiment on a small cube of smart concrete fabricated in our lab, where in red you see the applied strain with a compressive machine, and in blue you see the electrical signal outputted by the material. You clearly see that there is a very good correlation between the two. Are you seeing my pointer right now? I think so, right?
Yes.
Okay, thank you. So the way in which we transform normal concrete into such a very good strain sensor is by engineering its nanostructure or microstructure. So what we do, we include within the matrix of the material conductive inclusions, mostly monodimensional inclusions, like carbon nanotubes, for instance, or carbon nanofibers. Sometimes we can also work with carbon black, though carbon black is let's say, spheroidal, graphene, or different types of graphite. All these inclusions, what they do, they create inside the material a sort of network which allows the material to become a strain sensor. I will show you how in a while. But why is this so attractive? It is attractive because the material can generate a more direct response to the damage. The material is naturally integrated in the structure because it's the material itself that is a sensor, or it's highly compatible. If I use a piece of smart concrete within a larger structure, the compatibility between the smart concrete and the overall concrete will be just optimal. And I can have the material provided with novel functionalities like the strain sensing, but also an improved mechanical performance. And in general, I can integrate the ability to sense information all through the structure. The way in which the smart concretes we're working on work is very simple, basically. They are essentially strain sensors where the sensitivity comes mostly from the piezoresistive effect. These materials can also be used with different mechanisms of sensitivity, but this one I would say is the most useful and attractive one. So basically the material, like a monodimensional conductor, when it is strained, changes its overall electrical resistance in a way that is proportional to the strain through a proportionality coefficient, which is called the gauge factor. The theory says that the gauge factor is 1 plus 2 times the Poisson's coefficient plus the relative change in electrical resistivity under unit strain. So this is known from electrical strain gauges, for instance, where the third term is basically negligible. In fact, in strain gauges, we typically have gauge factor values which are around 2. In the case of smart concretes, instead, we work in this last term and we try to boost it as much as we can. This term is called piezoresistivity because it's the relative change in resistivity under unit strain. So how can we change this piezoresistivity? Is by engineering, again, the nanostructure or the microstructure of the material. So the continuum will not be made of one single phase. It will be made of 2 phases, a matrix and the inclusions, okay? And the inclusions can be conductive monodimensional inclusions like multi-wall carbon nanotubes I'm showing you here in this SCM picture. So when I add an increasing amount of inclusions, like in this graph, this is carbon black, for instance, and I plot on the y-axis the resistivity of the material, there is an amount of inclusions where the resistivity drops significantly, orders of magnitude. The amount of change we have depends on the type of fillers we use. This drop, this region where there is this jump is called the percolation threshold. It's the amount of the inclusions that makes the material percolate and become a conductor. At this quantity, basically, we have an optimal strain sensor. We have a material that has largest gauge factor with largest piezoresistive contribution and has a very nice linear response. So this is a percolation curve obtained in our lab for smart concrete. And as a matter of fact, there is literature that shows that we can predict the percolation threshold analytically as function of the properties of the fillers and the matrix, and most of all as a function of the aspect ratio of the fillers. So basically, the larger the aspect ratio, which is the ratio between length and diameter, the lower the percolation threshold. So basically, if we use inclusions that have high aspect ratio, we need less inclusions to gain a very good sensor. What is very, very important is that we need to also optimize the dispersion of the fillers and actually be careful in achieving a good dispersion. Otherwise, the sensing behavior will not be very good. So most of the work we have done on smart concretes is based on the use of multi-wall carbon nanotubes, which are excellent fillers due to their high aspect ratio for this kind of composites. However, multi-wall carbon nanotubes pose one formidable challenge, which is the difficulty in dispersing them in the smart concrete. The way in which we do that is by dispersing the nanotubes in water first, and then adding cement and aggregates to generate the material. However, this dispersion may require procedures like magnetic stirring or like sonication or like mechanical mixing, which may be difficult to be applied when we deal with large casting volume. So we have done a lot of work in trying to optimize the dispersion of the nanotubes without using magnetic stirring and sonication, but just using a proper amount of mechanical mixing and maybe using some dispersants, some chemicals to help the dispersion of the nanotubes in water. Doing it properly, we obtain nice suspensions of nanotubes in water like the one I'm showing you here. And finally, this is a comparison of a plain cement paste and a cement paste with just 1% of nanotubes with respect to the weight of cement. You clearly see the big change in color due to the fact that the nanotubes have a large ratio between area and mass. So here is an example of inspection of nanotubes dispersion in water and inspection of nanotubes dispersion in the matrix. These kind of SEM pictures are really important because you have to be sure that the nanotubes are well dispersed. This is, of course, done after the water dries. And also, you should inspect the hardened matrix of the material to be sure that the nanotubes are not broken, do not get broken after the mixing process and the separation process. This is really, really important if you want to exploit all the nice features that the nanotubes can provide. Here I'm showing you here an example, of increasing magnification of SEM pictures of nanotubes, showing you how small they are and what kind of network they tend to create when they are agglomerated. Here on the top is an example of a bad dispersion. You see coherent structure of nanotubes all agglomerated. On the bottom, you see an example of good dispersion. When you have a bad dispersion, you will observe that the nanotubes separate pretty fast from the water. They just separate in the order of minutes. When you have a good dispersion like this one, you will see that nanotubes will take days, hours, or maybe days to separate from water so that the light on the back will not pass through the specimen. So let's come on how we do the measurement with these materials. We have understood that the materials is piezoresistive. It's a strain sensor and can be a damage sensor. The way in which we extract this information from the hardened material with the nanotubes is by using externally attached electrodes. I have to say that this is probably the main bottleneck of the technology so far. There is research trying to get rid of the electrodes, which I think is one of the most promising avenues for research in this field. If we may do contactless measurements of strain, for instance, using lasers, that would be really a great step ahead. Anyway, most of the research we have done was either using a 2-probe or a 4-probe measurement approach. In the 2-probe measurement approach, we have 2 external electrodes attached on the material. We apply a constant electrical voltage at the 2 electrodes. We measure the current crossing the specimen, and we obtain the resistance of the specimens through Ohm's law. In the 4-probe method, instead, we apply at the 2 outermost electrodes a stabilized current, and then we read the voltage drop across the internal electrodes. The 4-probe method requires 4 electrodes, but has the advantage of being less affected by contact resistance. A very important, let's say, achievement we did in this field was that of reducing the noise when using a 2-probe method. When you use a DC power, actually, to power your sensors, you have a big problem with the noise. And also, you have a big problem with the polarization. The polarization is the tendency of the material to show an apparent increase in electrical resistance due to the orientation of the dipoles within the material. With this approach we have developed here, which is based on coaxial cables, we have been able to eliminate the noise from the sensor through a cancellation of the noise by means of a cable where the internal core of the cable and the external part of the cable, they are coaxial, like we do in accelerometers. And basically the noise that you have in the internal part and the noise that you have in the external part, they cancel out. Here you see an example of a signal measured like this on a vibrating beam that I will show later on in an experiment. Another great step ahead we did in this same field was that of developing an approach for measurement, which is not direct current, but we call it biphasic direct current. So basically, with respect to the previous case, we are not applying a constant voltage to the two external probes, but we are applying a voltage which changes in time through a square wave, like I'm showing you in this graph here. So basically, the voltage is applied with a plus minus value with a square wave of certain period. So we are basically discharging and recharging the sensor every time. In this way, we actually get rid of the polarization. We get rid of the fact that the material gets charged, because basically every time we charge the sensor, then there is a part of the signal where we discharge the sensor. We measure the electrical current flowing through the sensor during the application of this square wave, and then we take the 80% of the period of the square wave as the point where we extract the resistance of the sensor. In this way, we get results like this. You see, these are values of, this is the sensitivity of the sensor in terms of change in resistance versus applied strain as a function of the frequency, which is almost constant. But more importantly, we get signals in time, which are like the one showing you here in the bottom right. So basically, in DC, we have a resistance that increases in time due to polarization. But when we do a biphasic DC, so our approach with a square wave having different frequencies from 1 Hz to 400 Hz, you clearly see that the signal has no drift, is stable in time, which was our goal. We also check that the optimal duty cycle for obtaining this stable signal is in fact 50%. Which means that the amount of time the signal stays in the discharge region is the same as the amount of time the signal stays in the measure region or charge region, and that the voltage, negative voltage is equal to the positive one. We are now developing, the electronics to do this kind of measurements. Instead of using off-the-shelf and very expensive equipments, to do this kind of measurements, we are developing internally to our group what we call a smart material electrometer. We have a postdoc in my group who is an expert in electronics who is doing basically this development. The smart material electrometer is an electrometer that can do 2 probe or 4 probe measurements, that can do DC and that can do biphasic DC measurements, and that can do that in multi-channel configuration. So we can measure from many sensing units, basically. And we are doing this with low-cost electronics so that the overall cost of the smart material electrometer is around a couple of $100, while what you take from the market can be orders of magnitude more expensive, at least in the order of thousands of dollars at least. So here are some results that we obtained with our smart concretes. I'm showing you here on the left some percolation curves. These are referred to paste, mortar, and concrete specimens with different types of, they are all with nanotubes, but with different types of mixing procedures. And you may see that in some cases, the percolation curves are really, really clear, with jump in conductivity of 3 or 4 orders of magnitude. When we have a clear percolation is when we have a clear sensing, like I'm showing you here. This is the same result I was showing you before, and we also have a very good linearity between change in resistance and measured strain, as you see in this graph. We have also studied a lot the strain response when the loads are dynamic. Since our group is very active in vibration monitoring, we have studied the response of these smart materials to vibrating strains, so dynamic strains. Actually, and we are among the very few groups that have done this in the literature. Actually, these sensors work pretty well when we try to measure vibrations. They work even better than we try to measure when we try to measure quantities that vary slowly in time. But the key here was what I've shown you before, the use of coaxial cables to remove the noise. So here you see the response of our sensor to an harmonic input with single frequency. And here you see the response of our sensor to a sweep of frequencies, where the red curve is the strain measured with strain gauges, and the blue curve is the electrical response of the sensor. If we plot the amplitude of the response as a function of the mechanical frequency this time, not the electrical frequency, you see that the frequency response curve of the sensor is almost constant, actually a little bit increasing, which means that the sensor works pretty well to measure high frequencies, even better than low frequencies. One limitation we have when we use these sensors for dynamic monitoring is that if you apply an harmonic load, the response will still be periodic, but will not be harmonic. So it will comprise, like in this case, superharmonic components. And for this, I will have an explanation later on when I will talk about modeling aspects. So we have used this capability of the sensors to measure vibrating strains to demonstrate that we can do model identification of structures using cement-based carbon nanotube sensors. This is an old experiment. We did this experiment more than 10 years ago on a vibrating beam with attached smart concrete sensors, and we obtained the results that we have that I've shown you in the previous slide. Jing, I got a message from the system. You're still hearing me, right? Jing, you still hear me?
Yes. Yes.
Yeah, okay. Sorry, because there was a message. I don't know. So I was saying that this is the result I was presenting before with the hits of the hammer. So the vibration you saw before are the hits of the hammer you have seen in this video. So you see here the very good quality of the signal in terms of, let's say, signal to noise ratio. And you also see the drift in time due to the, basically due to the polarization of the material. Actually, with applying a high-pass filter, you can easily remove this drift and obtain a signal like this. Of course, you lose the average component, but if you are doing model identification, this is not important. And analyzing the spectral plot of this signal, you obtain the natural frequencies of the beam pretty well. So we demonstrated that we can do identification of the beam using this kind of sensors. This is another experiment where we have done similar application, but with the sensors being pre-embedded in the beam before casting. We have shown that we are better than strain gauges in measuring the strain under let's say a static load. Here is the static load, loading, then unloading, and loading and unloading. This is one person that was jumping, that was stepping onto this beam. And also the strain that we measure makes sense with respect to the theory that we expect from Euler-Bernoulli beam theory. More importantly, we could, doing an experiment like before, maybe we have less signal to noise ratio because the sensors are embedded, but still we have pretty nice free vibration signals extracted from the sensors. In black is the sensor, in red is the strain gauge attached on the sensor for benchmark. And we clearly see that we can identify the natural frequencies of this vibrating beam. We are now doing similar experiments on larger beams, including beams that are fully made of smart concretes. So this was about the measurement. Let's come now to other types of application and then the modeling. An interesting application is the bulk form, when the material is fully made of smart concrete. In this way, we need a multi-channel configuration to measure the electrical resistance across different pairs of electrodes along the beam, like we have done in this example here. The type of results you obtain are like this, where basically in each section you obtain more or less the same resistance, with larger resistances only at the outermost electrodes, which are affected by local, let's say, phenomena at the contacts. This kind of resistances we measure across the different pairs of electrodes here is pretty much sensitive to strain. Like in this case, I'm showing you an entire beam made of cement paste with multi-wall carbon nanotubes tested in a 4-point bending scheme. And here you see the change in voltage in different sections as a function of the load. You can clearly see that different sections respond more because, of course, the strain will be larger. You can see the piezoresistive effect, where the change in voltage, which means the increase in resistance, increases with the applied load. And then when a crack appears, you have something going on. So this curve goes down and this curve goes up. Because internally the material is sensing the damage, not the strain. And so you have changes in local measurements you do of electrical resistance. It's important that the crack was audible through an audio system here, but the change was already spotted before. So we are sensing the damage when it's a micro crack, when it's not visible and it cannot be detected by, let's say, acoustic emission, at least not easily. We have applied similar concepts to bidimensional elements like this plate that we have subjected to controlled impacts. the plates was equipped with many electrodes, was made of cement paste with carbon nanotubes. And again, we obtain an overall electrical resistance of the plate, which is sensing to the damage, which in this case is the number of impact. Already at a very low number of impact, we have an overall resistance of the plate that is increasing. And locally, we have values of resistance that are decreasing and values of resistance that are actually increasing. Overall, it's increasing. Locally, it can be increasing or decreasing. So this is also very sensitive to the damage, well before the damage is so large, like I'm showing you here. But if we want to understand and model how these materials behave, then we need, interpretation models. So I'm proposing you different strategies we can use to model the behavior of these materials. The most powerful one is based on micromechanics method. Micromechanics approaches are basically analytical approaches that try to estimate the overall average properties of a composite, starting from the properties of the matrix and the inclusions, and considering the way in which the inclusions are distributed within the masonry. So these micromechanics methods are well known to predict the elastic properties of composites and have been used by our group to predict the sensing, the electrical conductivity and the sensing properties of the smart concretes. So in micromechanics approaches, I will at the end give you a list of papers we have published, and if you are interested, of course, in the question time, you may ask, and I will also be very pleased to answer emails even later on. So in micromechanics approach, we have the possibility of considering all the physical phenomena that are happening inside this kind of composites. So how does an electron pass from one nanotube to the other one, or one inclusion to the other one? There are different mechanisms. The most important are electron hopping, which is a quantum mechanics phenomenon where the electron jumps from one nanotube to the other one, even if they don't touch each other, winning an energetic barrier. And of course, the probability of having the electron jump increases when the distance between the nanotubes decreasing. And when we increase the amount of fillers and we reach a situation where fillers start to be in contact with each other, it's when we are percolating. So basically, after the percolation, all the fillers will be connected and there will be a continuous network inside the material. Below the percolation, basically, we have the coexistence of two types of phenomena for the movement of electrons. One is by the nanotubes that touch each other through conductive network, and the other one is actually the electron hopping. So we can predict the conductivity tensor of the equivalent conductivity tensor of the composite, assuming it to be, let's say, considering a representative volume element of the composite that is statistically representative of the overall material, through mean field homogenization theory, and particularly to the Mori-Tanaka extension of the problem of Eshelby's considering single inclusions. So the main equation is this one, where the conductivity tensor is actually a mixture of the conductivity tensor of the matrix plus the fraction of inclusions that multiplies this quantity, that is the conductivity tensor basically of the inclusion. In these integrals you have to take, there is a function A, which is called the electric field concentration tensor, and then there is a function ODF, which is the orientation distribution function, that consider the possibility that the nanotubes are not oriented uniformly, randomly, but they might be oriented preferably in one direction respect to another one. So in this nice analytical framework, we have included some key aspects that we found in these materials. First of all, the nanotubes are not straight. They are kind of twisted. So we have included waviness of the nanotubes inside the formulation in a very simple equivalent way. We also consider the fact that the nanotubes tend to agglomerate. Even though you do your best to distribute the nanotubes uniformly, you will still have some bundles within the material. So part of the nanotubes will be aggregated in bundles and part of them will be free inside the matrix. And we also consider that. And then we model the interaction between the nanotubes through a special, let's say, interface element and interface equation. So the way in which, for instance, we consider the bundles is this way. We have two quantities that are dimensionless. One is the ratio between the volume occupied by the bundles and the overall volume of the representative volume element. So when you have this quantity equal 1, it means that the bundle is actually the whole material. And then zeta describes the amount, the volume of nanotubes that are dispersed in the bundles with respect to the total volume of nanotubes that we have in the representative volume elements. So if this goes to 1, it means that all nanotubes are in the bundles and they are not in the matrix. Then this approach, since it merges electrical conductivity with mechanical properties, I have not shown you the equation for the strain and stress tensors, but this is known from literature. Since we merge these two aspects, we are also able to predict the way in which the electrical properties change with the applied strain. For instance, when there is a uniaxial strain applied in one direction, what will happen is that the nanotubes will tend to orient more in that direction. So we can consider that through an orientation distribution function that assumes values that are different from 1. Also, when we apply a strain, the volume of the material will change, which means that the average distance between the nanotubes will change. This will increase basically the probability of having electron hopping for the nanotubes that are not in contact with each other, and will also reduce the contact resistance between nanotubes that are in contact. So this kind of model could fit pretty well our experiments. I'm showing you here, for instance, an example of effective conductivity of smart concrete as a function of a quantity of multi-wall carbon nanotubes. You see different analytical curves associated with different properties of the nanotubes, different values of waviness, different values of agglomeration in bundles. And then you see experiments with these squares. You see that the waviness and the agglomeration of the nanotubes are really important to model this behavior. We don't have a clear percolation because our distribution of the nanotubes is not optimal. So that's why if you consider a perfect percolated composite, you will get results that do not match with the experiments. We have done this for several types of materials like paste, mortars, concretes, and always being able to interpret the response of the material, except for very strange outliers here. This is the effect of the dispersants we are using for dispersing the nanotubes and the air entrapment due to the nanotubes. So when the nanotubes are in a small amount, you may actually have a lower conductivity than when they are not dispersed in the matrix, but that's only for very small amounts. And we can also check what are the, let's say, most sensitive parameters that affect the overall conductivity of the material by doing a sort of sensitivity analysis. So you see, for instance, that the conductivity of the matrix and the aspect ratio of the nanotubes, as well as the waviness of the nanotubes, have a large impact on the final conductivity. But it's more interesting when we apply the framework to predict the strain sensing response of the materials. So we can apply the framework, for instance, to analytically predict the gauge factor as a function of the quantity of nanotubes. So here you see analytical curves, and then you see these black dots here, which represent experiments. So you clearly see that we tend to have an optimal gauge factor at the percolation, and we get curves, analytical curves that make much sense with respect to our experimental findings. We have also extended this micromechanics approach to three-dimensional strain and stress conditions, where we have demonstrated that actually the material is more like a volumetric strain sensor. So what we measure is actually a change in volumetric strain rather than a monodimensional strain, and that shear strain basically does not really affect the resistivity of the material. So basically the material is not sensitive to shear strains. Another modeling approach which I consider very useful, by useful when we want to do signal processing, is that based on lumped circuits. So basically lumped circuits are electrical circuits that equivalently model our material and that can be used to predict the time varying response of the material. The simplest case we have studied was this one, a combination of a resistor and a capacitor in parallel, where the resistor is strain sensing. We have applied this one, for instance, to reproduce the response to a constant voltage, so basically a free response. So the phenomenon of the charge accumulation in the material, so the polarization phenomenon. And you can clearly see here that the experiment in red and the model in black match pretty well. We also have used this equivalent circuit to predict the dynamic response of the sensor. However, we found that if we do that, we obtain analytically a response whose amplitude decreases with increasing frequency of the mechanical load. This is not what we expected. This is not what we observed from the experiments. So we discovered that actually the material contains a little bit of piezoelectric effect. Piezoelectric means that when it's strained, the material provides a little bit of voltage, even if it's not power. We found that adding this piezoelectric component within our lamped circuit and also making the circuit a little bit more general to also consider changes in capacitance due to strain, so the material is also piezocapacitive, and also including an electrode and interface path between electrodes and material and between nanotubes and matrix, we could obtain a generalized lamped circuit equation which matched better than any other model our experiments, also was able to reproduce the frequency response curve that was increasing with the frequency of the load, and also was able to reproduce the presence of superharmonic components in the dynamic response when we apply an harmonic loading, which I was commenting at the beginning. Another suitable modeling approach that is very useful when we want to do crack identification is using resistor mesh models. This is an approach is a sort of lamped circuit approach that we can use when the material is applied in bulk form. So essentially, when we use the material in bulk form and we have different contacts inside the material and we measure voltage drops across different pairs of electrodes, and then with a shunt resistor we measure the voltage drop through a non-resistor to obtain the current, and so I can retrieve the resistance from these pairs of electrodes. Then I can model the continuum here with a mesh of resistors, where the red resistors are the contact resistors at the two outermost contacts. Then there are normal resistors, and then there are resistors that of which I increase the value in such a way to obtain a match with the experimental response. And when I find resistors like this in an optimization procedure, in an inverse problem that tries to fit my experiment, I will be able to identify the crack, because I will find the large value resistors in the regions where the crack is actually passing. I'm showing you here an example. This is a specimen with different pairs of electrodes. This is the voltage drop I measure across the 4 different pairs of electrodes along the specimen. In green, I have the experimental data for the specimen in LT conditions, and in red, I have my analytical model where I fit the values of these resistors through an inverse, solving an inverse problem like this. Then I apply a cut to the sensor here. When I apply a cut, I have a mismatch between the model and the experiment. But if in the model I include the cut here, where it is exactly located, then I obtain a good match with the experiment. So this means that I can use this kind of modeling for a direct identification of the cracks. I run this again. Only when the high value resistors in the analytical models are placed in the exact position where the damage is occurring. Now I create the cut here. So in red, you will see where I put the crack in the analytical model. Only when the crack in the analytical model is actually in its actual position, I will get a good match with the experiment. We have applied this also in more complex examples. In this case, I show you how a voltage drop increases with the cut length. And here is the experiment I was showing you before regarding the 4-point bending test on the beam made of smart concretes with carbon nanotubes. Recall that I showed you this change in voltage drop increases with the applied load, and then changing in certain sections when the damage initiated. Actually, with a model like this, with a resistor mesh model, we were able to actually reproduce this behavior. Here you see a comparison between experimental results with continuous lines and analytical results with dashed lines. You see that the analytical results follow pretty well the experimental one. At least they have the same tendency. Maybe they do not really match well, but when the red goes up, the experimental goes up, also the analytical goes up, and when the black experimental goes down, the analytical experimental goes down. So at least we have something that resembles pretty well what we observe in practice. We apply the same fitting procedure also to this two-dimensional plate example here. And this is the values of the resistances we obtain by fitting. So this is a map of these values of the resistors by fitting this map before the damage. And this is after some damage. If I take the difference between this and this, I obtain the plot on the bottom right. So you clearly see that I can spot the regions of most prominent damage, let's say. It's a sort of tomography where at least I can spot the regions of larger damage when the damage is not strongly visible. And if I inspect the value of one resistor with the number of impacts, you see that it increases with increasing damage level. Okay, this was pretty much our past research on smart concretes. I will now spend 15 more minutes regarding the future work that we are starting right now, and I will tell you a little bit about different projects going on in this research line within my group. First of all, 3D printing. 3D printing is a very attractive technology, and we think that 3D printing as smart material is really something very appealing, because we can use sensing properties where we need them. So basically, when you print a structure, there is a critical part. In that critical part, you will print a smart concrete instead of a normal concrete. Also, these kind of 3D printed structures that can be very challenging from a structural point of view. So we may try to reduce the dimensions of the elements, but we need to know what is the strain condition within the elements. So I need sensors. And what best than a sensor that is built with the same material of the structure when the structure is built? So we are doing right now, we are playing right now with cement-based materials with carbon microfibers, not nanotubes. This is a small 3D printer in our lab, and here is a video of a sensor we were printing just a few months ago, just to show that we are at the beginning of this, but we are already able to print the doped material and to create sensors, at least to test piezoresistivity. So I'm showing you some preliminary results on this. We have been doing this experiment together with colleague Professor Simon Laflamme from Iowa State University. We have investigated the quality of the dispersion of the microfibers through heating the sensor. So if the sensor heats on this homogeneous way, then I have a temperature distribution like this, that is at least bimodal. Then it means that the dispersion of the microfibers is not good. Instead, when the material heats in a more homogeneous way, with the temperature following a monomodal distribution, then it means that we have a better distribution of the microfibers. And when the distribution is good, actually these 3D printed materials can be very good strain sensors. Here I'm showing you some example of specimens where you see relative change in resistance versus strain, in some cases with pretty nice linearity. Another very interesting application, in our opinion, is shooting these smart concretes to construct structural elements. So this was the result of a large project that we ended recently. In this project, we were investigating earth cement materials. So materials where 2/3 of the cement is substituted by raw earth to obtain sustainable material. But then we added carbon microfibers to improve a little bit the tensile behavior, but mostly to obtain strain sensing capabilities. Here you see, for instance, a tensile test in 3-point bending, where you see there is the failure in tension, and here you see that there is the jump in conductivity. So the material senses the damage. We developed the material up for spraying, like we are showing in this picture of the test we did in the lab. And we sprayed an entire vault, let's say a shallow vault, like this one, made of this smart earth concrete that we tested until failure. First, we tested with uniform load coming from water, let's say filled elements, and then applying a force at 1/4 of the span of the vault. Here is the experiment where we apply the force here, we measure displacement with LVDT sensors in these points, and we measure voltage drops across these pairs of electrodes here. Electrodes have the same length as the width of the volt. Here you see a video of the volt being tested to failure. This was a displacement control test. So this is a time-lapse video, but the test lasted several hours. You clearly see that we have a good ductility because we have a tie rod here, and so we are able to form a 4-inch failure mechanism. And we were measuring with our smart material electrometer the voltage drops across the different pairs of electrodes all through the experiment. Here I'm showing you what we measured in the 4-channel in terms of relative change in resistance versus time during the test. You clearly see that as long as I was loading the volt, we show increases depending on the channels, of course, of the relative change in resistance. In channel 3 and channel 4, which is where the crack is located, we see a clear jump when the crack started to initiate, and then we have an evolution of the relative change in resistance that increases with the applied load. So to interpret what we are reading, we realized a multi-physics model a computational model in Abacus, where we model the mechanical behavior of the material through the concrete damage plasticity model, so considering damaging in compression and in tension. And we also included, of course, the piezoresistivity of the material, so relative change in resistivity proportional to the trace of the strain sensor, so basically proportional to the volumetric strain. And we reproduced let's say, the change in conductivity with the damage through this, what we call permeability. So the permeability is a factor that multiplies the conductivity, and is a factor that goes from 1 to 0 following these curves that you need to identify based on the properties of the material, as a function of the damage variables in compression, in tension and compression. So basically, in this way, we are able to model the material's ability to sense the damage. Here is an output of the simulation. You clearly see that the collapse mechanism is the same as in the experiment. And here is a plot of the voltage distribution within the specimen. So in these graphs here, we compare with continuous lines and with dashed lines. It's not really well visible, but I think you may, let me take a pointer here. Okay, like this. You can see here continuous lines and dashed yellow lines, same continuous blue lines and dashed blue lines, and so on, where the continuous lines are the experiments and the dashed lines are the simulation results. These in terms of force displacements measured by the LVDT sensors. Here you see an improved plot of the same quantities. Here you see the electrical responses that we measure from our 4 channels in the experiment, and here you see the same quantities that we obtain from the numerical simulation. So there is a clear relationship between what we have on top and what we have on the bottom, and if we compare them, we have good agreement between simulation and experiment. So we found that to obtain these kind of results, it was very important to model the rebars inside the volt. And this simulation shows that we can actually model with multi-physics approaches the response of these materials and use the models for damage identification. Another important project we just started is the SMS Safest project, which is an Italian advanced grant from the Italian Science Foundation, which funded this research that will last for the next 5 years, which is devoted to developing an innovative approach for monitoring masonry structures subjected to earthquakes. You know that masonry structures form the majority of our cultural heritage structures, which are especially vulnerable to this kind of loading. So the idea is, instead of relying onto traditional SHM, which has bottlenecks like scalability, durability, transmission problems, cost, aesthetics, and so on, the idea is to use smart sensors, as I was discussing before. So how do we want to use the smart sensors? Basically, we aim to develop smart bricks. Smart bricks are bricks which are very similar to normal clay bricks, but they contain inside, there is a change in their microstructure through the use of, for instance, metallic conductive fillers, which can work similarly to the smart concretes. Here, the behavior is a little bit more complex because we have more metallic phases within the material. But in any case, we can get a response like this. This is the applied load in yellow. This is the measured strain on a brick tested in the lab, this one. And this is the electrical response of the brick. You see, of course, when then the compressive strain increases, the electrical resistance decreases and vice versa. And I was saying that the behavior is a little bit more complex because here we have two-dimensional electrodes. So we need to consider a little bit of contact sensing and contact resistance, which is also sensing, and internal sensing. Also, we are developing what we call smart mortars, which are lime-based mortars or cement-based mortars with suitable inclusions to obtain the ability to sense the damage. In these videos, which are really preliminary, hopefully they will start, you will see, let's see if they start. Let's see if they start. You will see at certain point a change in color in the video, which is when in the small wall being tested, a damage develops within the mortar. Let me see why this is not working. Maybe I can have it run like this. Maybe not. I don't know. This was working before the talk. Sorry. Anyway, it's okay. I don't know why this video was not working. Maybe in the question time I will be able to make it work. Maybe now. Okay, now you should see it. It's getting dark. You see, as time increases, load is increasing. You should see at certain point that in the bottom left part of, yeah, there you go. You have changing color. This changing color is when the crack forms, and the crack is not visible. It's a micro crack within the mortar layer. Now it plays again. So this is very preliminary, of course, but it's just to show you what we would like to do. So developing bricks that can measure strain and mortars that can measure directly the damage. Finally, last application I like to mention is doing smart pavements for weighing motion. So these are smart pavements that can sense the loads coming from a vehicle, and we can use this for a high fidelity, low cost weighing motion of the vehicle. We have developed the algorithm that does the weighing motion. We have developed the material, which is an asphalt with carbon microfibers. We have developed the electrical configuration and the software to do the analysis. Here you see typical signals and the signals reconstructed with our algorithm, where the parameters of the algorithm are actually the weights of the different axes of the vehicle. Here you see the field test, video of the field test, a truck passing over our field test, the type of electrical signal we get, where we measure all the peaks related to the different axes. And here is a comparison of the weight that we estimate for different trucks compared to the real weight. The estimated weight is in blue, the real weight is in black, and you clearly see, because we had the possibility of measuring the real weight, and you see that the accuracy is pretty good. So here what we would need to do now is developing, working with different velocities of the truck, and also working with temperature changes. So with this, I'm done. I will not say conclusions, if not that I try to show you how smart concretes are really an attractive technology, and also different branches of this research and where we are going right now within my group. I will provide the slides, or maybe you have the video of this webinar, so you will see. That's why I put all these papers. You can see what we did, basically what we published on this topic. And to close, I would thank the main sponsors of this research, which is the big grant I was mentioning, the SMS Safest project, and also this project, which is a project Vitality in the frame of the National Recovery and Resiliency Plan after the COVID pandemic. And I would like to acknowledge the help of all my group members that you see here, that of course have collaborated and collaborate and are collaborating to this research. And with this, I thank you.